Okay, so RL via you will have both DC current also flowing, AC current is also flowing. DC current only will cause power loss, AC current fills the amplified current. Okay, so if you want to remove the DC current which is flowing through RL, best option is go for transformer. So if you put a transformer at the collector side, so RL will be present as the secondary of your transformer, so no DC current will be flowing through your RL, so the power loss is minimum, so the efficiency can be improved. So two reasons why we are going for transformer coupled power amplifier is, one thing, I am going to increase the efficiency of the amplifier by using transformer. So transformer provides a perfect coupling and isolation between the various modules of your device. Second thing, the power loss can be minimized by isolating RL from the collector side. That is what I am doing it here. In an ideal transformer, the resistance of primary winding is 0, so the power loss is 0. So the transformer will ensure that the power loss is going to be 0 when you are going to introduce this into the power amplifier. So you are going to use a transformer to transfer the substantial amount of power from the collector to the load. And one more thing, this transformer will act like an impedance matching device. So whatever be your load, whatever be your source, the transformer would ensure that the power is transferred from source to your load. So this significant power transfer is possible using a transformer. So otherwise, internal resistance only you have to use, but the drawback of using a resistor is most of the power will be lost in the resistor itself. So effective amount of power which is going to reach your device or load is going to be very, very minimal. So please understand that the use of transformer will reduce the power loss and it will also increase the efficiency of my device. So instead of having one transformer, I'm going to have a pair of transformers, one at the input side and one at the collector side. So input side, I'm isolating, this transformer will isolate the source and the base. Okay, and this transformer at the output side will isolate the collector and the load. So when isolation happens, the circuit becomes stable, power loss is minimized, high effective coupling takes place, efficiency is also going to be very, very high. So secondly, RL is present in the secondary of your transformer. So when you refer that to primary, you will get RL dash equal to RL by N square. So these things you have studied in basic electrical engineering where you have studied about transformers, right? So when you want to shift the load from secondary to primary, you have to divide by N square, where N is going to be called as the turns ratio. N is small n is given by N2 by N1. N2 is the number of turns in secondary and N1 is the number of turns in the primary. So by taking N2 less than N1, N can be made very much less than unity and RL can be made larger. So if N is very small, RL will be very, very larger. So effectively, you can connect any value of load resistor to your power amplifier for effective coupling of power from the collector side to your load resistor. Okay, so this is the use of a transformer to actually boost the efficiency of your device. So now efficiency of class A amplifiers. So we are going to derive the efficiency of class A amplifiers. To determine efficiency, you have to see what is the various power which is involved in the circuit. So you have a DC power given by VCC into IC, so which is going to be a loss for you because this is required for biasing your circuit. So amplifier is supplying a pure supplying power to the resistive load. The average DC supply is VCC into IC. This is going to be lost because of biasing, and the power absorbed by the circuit is IC square into RL plus IC into VC. So this is going to be the power absorbed by the circuit where everything is in RMS value. IC and VC are the RMS values of voltage and current. RL is going to be the load resistance. So if we are going to take PdV as the power dissipated by various active device which you have inside the device, then we can say the total power input should be equal to the sum of all the powers. So VCC into IC is the total input DC power what you give, that should be equal to all the other powers. So VCC into IC will be equal to IC square RL plus IC into VC plus PdV. PdV is the active power dissipated by the active devices. Why we are having two components in the output side, IC square into RL plus IC into VC is, see, this IC square into RL is the DC value of current which is flowing in the collector side, which will give rise to a loss. VC into IC is the actual AC power, which is the amplified version of your input. So we have two components at the output side along with one common power dissipation factor. We take it as PdV. So by law of conservation of energy, input should be equal to output. Input is VCC into IC. Output is going to be IC squared into RL plus IC into VC plus PdV. So under DC conditions, if you see this PdV, under DC conditions, you can substitute VCC equal to, this PdV will be 0 under DC conditions, okay? So you can cancel one IC. So VCC will be equal to VC plus IC into RL. So in that case, you can write the PdV as PdV equal to VC into IC minus VC into IC. It is going to be 0. PD is going to be 0. When you substitute for VCC as this expression, you will get the value of PdV is going to be 0. Under